Hi, this is Robert Bolaños. Welcome to the analysis and design of a power supply or flyback. This is video 24, the Opto coupler. It's kind of like a little follow-up. What I'm going to try and do is do a quick review and then of what we covered last time as far as the TL431 and the Opto coupler. And then the main point that I want to get is that what we're trying to do is we're trying to build a average model. Okay, and we need the average model because that's how we plot or set the loop compensation. Okay, and there's two models, SPICE models. There's the average model, which is what we used to use to do the loop compensation, and we also have the switching model. Okay, and the switching models are different. They're basically almost impossible to do an AC simulation, so it cannot be done. Okay, basically can't do that. There is an exception, or I shouldn't say that it's almost impossible, or that's not impossible. It is, but it just the simulation time takes incredibly a long time. There's only two simulators where you can do the switching model and do the AC Bodhi plots from them, and that's I believe Simplex or Simtress, where you can do that. But the main idea is that if you have top spice or any of your spice, you need the average model, and if you have the average model, then you can do an AC plot or Bodhi plot, and you can also do some transient simulation. Okay, so let me just go back and review a little bit what we did. Okay, here is the schematic, and mind you, this is a average model. Okay, and we're using Jack's model to simulate the PWM, the MOSFET, and the flyback itself. So that's the averaging model that I used, that Jack Alexander taught me. Okay, so I made some assumptions, and the assumption is based on looking at the block diagram of the 1843. There's a compensation pin, and we assume that it was 3.1 coming out of the compensation, and then when you do the simulation or the analysis, for this to be 3.1 at this point, basically at the emitter of your Opto, we would need 1.9 volts. Okay, once you have 1.9 volts that set, okay, then we can select the resistor based on the current that we're going to flow through this here. Okay, and to do that, to select this resistor, we use this equations, and that's based on the CTR beginning of life. Okay, basically that's when your maximum CTR is at its highest. So based on that, you get the value for this resistor, and you set this current through here. And I made a statement that basically once you set this current, that this will remain constant, and also if this current remains constant through the entire life of the power supply and through aging, this voltage will also remain constant. What will change is this current. This current will vary as you have aging in the LED. Okay. As a matter of fact, as you age, the CTR will decrease, but the current will go up. Okay. So that's the statement that I was trying to make. And then the only other thing that you really have to calculate is really the value of that resistor. Okay. And that my simulate computer's acting up a little bit. Okay. And by that, you made an assumption that the CTR is going to move from beginning to life to end of life, and therefore the current will increase. So in this case, at the beginning of life, it would be 2 milliamps going through the LED, and then it will increase, aging to 30 milliamps. Okay, and with that, you end up with this equation that you can use to solve that there. Okay, so that's a quick review. Okay, and what I want to show is the average model, how you can use the average model to get a plot of your output filter, and then show how you can get a plot of the bandwidth in the optocoupler, and then also show the frequency response of your error app. And then at the end, you want the total loop. Okay. So now we're going to go ahead and compare. And let me see if I can zoom this a little bit. Okay. So here's both models. This is the switching model. And the switching model, you can always tell that it's a switching model because you have a flyback. Here's the transformer. Okay, if you look at the switching model, there's no transformer up here. So on the switching model, you're going to have a transformer and you have a FET or a switch. Here's my switch. Okay, and then this is my driver and this is the PWM. Now what I'm using is, and if you notice, and this is what's neat about TopSpice, it actually has a spice model, or actually let me show it here. It has a model for the UC 1843. Okay, now please don't ask me to send you this model because it's encrypted. I can't even take a look at it, so it can only be used within the TopSpice environment. So if I click and I try to look at the net list, there's nothing to see because it's encrypted. So this is the PWM that I'm using, which is based on an actual chip. Okay, so just want to make sure that everybody understands that. Now I do have a generic PWM and those will be available. Okay, let me go back. Okay, so now, like I said, this is the UC 1843, and then basically this part. Okay, what I want is make an observation that this part in the switching model is basically the same as that part. Okay, they're should be identical. Okay, and let me explain this. Okay, this part is inside the UC 1843. In other words, this line would be the FB, and this would be the comp. Pin. So basically you have and then there's an internal reference. Okay, so basically this is the same. And if you notice that resistor is this resistor is that resistor. Okay, so basically from here all the way to here is identical to there, and that this section, this little section, is represented or represents everything from here to here. So all this section is modeled by a voltage control current source. So this is a voltage control current source. Okay, so these are the differences. Okay, now remember, it's very difficult to do a SPI simulation using this model or actually I should say it's very difficult to do a AC plot with these switching model. Difficult. Okay, so the preferred way of doing this is using the average model, which is this. This is what you try to do, or the goal is to make up AC plot. Okay, now just to point out, here's the output filter. That should be identical to this. Okay, and at the end we're using this to switch to simulate a transient disturbance to prove that they both are equivalent. Okay, basically we're validating this model. Okay, so let's go ahead and do some simulations. Okay, so this is a searching model. So let me open up what's supposed to be its equivalent, and that should be the equivalent model. Okay, so the first thing that we want to do is we want to do the plant or the output filter. Okay, so to do that, we'll go ahead and okay, let's go ahead and you have to do a SPICE statement, and in SPICE you basically click the insert object. In this case, you would type in pound calc, and then you name loop. Calc, and you define loop equals parenthesis v out divided by v in. Okay, and put everything in parentheses. Okay, it's basically, that's what you do. Then once you have this defined, then you want to plot. Okay, so you want to plot the dB of this equation, and you also want to plot the angle of this equation. Okay, so this equation is looking for two nodes. It's looking for V out, which is this, and V in, which is that. So if you notice, we put these 2 points across a 10 ohm resistor, and I refer to this as a injection resistor or a venable resistor. This is okay. The reason was Dean Venable was the one that popularized the measurement of the Bode plot using his frequency response analyzer. So that's why I call that the Venable resistor as well. Okay, so once you have the resistor, then the next thing you have to do is you just type in a voltage source. So in this case, you press insert V. Okay, and you insert it, and when you double click, you don't put anything as, or actually you can put 0 volts. Okay, and then you enable and you put a 1 here. Okay, so basically you put in an AC volt there, so you have that. So once you have this, then you can do a signal. In other words, this will introduce a wiggle or a disturbance. That disturbance travels through the feedback, through the optocoupler, through the this op amp, and then through the voltage control current source, and it returns back here. And what it does, that wiggle or that sine wave is compared with this sine wave, and you compare the amplitude, which is what I'm doing here, and I also compare the angle. Okay, so by doing that, you can get a Bode plot. Okay, so I'm just going to go ahead and run it. This will give you the total response. In other words, it will give you the response through the entire loop. Okay, so this is what you want. This is the gain of the loop, the total loop, and where it crosses 0 dB, that is the bandwidth. They call that also the crossover, and that's approximately 14 kilohertz. So then right up where it crosses, you measure the phase, and that is about 100 degrees, and that would be your phase margin. So where you cross the 0 dB, the amplitude, the phase is the phase margin. Okay, so typically on a good power supply, the minimum that you can get away is 45. Most power supply have 60 degrees. That's good. So you should never go below 45. 45 would be somewhere like right there, close to there. So in this case, we have plenty of phase margin. This would be a very stable power supply. Okay, so the next is you want to know where does the phase cross the 0 dB point or the 0 dB degrees, and then you measure the gain, and typically you want this to be negative 10 dBs lower, and this is called the gain margin. Okay, so let me just put gain. Okay, this would be the gain margin. Okay, and then this point up there would be the phase margin. Okay, so those are the two critical measurements that you need to do in a power supply. Okay, so this is the total. Okay, so before you even get to here, you can take readings of subsections. Okay, and the first subsection that you want to do is you want to take a plot of your output filter. Now your output filter should look something like this. You're going to have a pole and typically this is your pole. That's 2 pi, your load, and your output filter. Okay, and then you have a 0, and that 0 is typically there, and this should be 0 dB. So to look at that, all you have to do is move this in. You move it out to the comp pin, and you can do that on a actual. I'll just leave it there, and I'll label this comp or as a text. Comp pin. This would be the comp pin. Okay, so if I put it there, I'll click, and there you have it. So here is your pole of the output filter, and then you have your 0. Okay, so this is because of the output filter. This is the output filter times the load. I have a load through this switch. The switch is modeled as 24 ohms. Okay, and if you do the math, 24 and then 47 microfarads, you get approximately, let's see if we can measure that. We'll do the negative 3 dB. That's about 144. Hertz. Okay. and then the 0 is up here, okay, close to about 20. So that's one plot that you want to do. Okay, so the next that you want to plot or get a feel for is the error app. Okay, and the error app consists of a integrator and typically you might have, if it's a third or actually a type 2 compensator, you'll get a 0 and a pull. Okay, and where do those come from? Okay, in this case, this is the error app is in here, and the combination of these two resistors will give you a 0. Okay, and let me go ahead. Let me go back. Okay. And let me backtrack a little bit. Although we are using a TL431, it looks and acts very similar to this. This is your error app. Okay, and then this would be your divider network. This would be V out. Okay, so this 0 is produced by the combination of these two. And these two, the roll off and this resistor, the integrator resistor, produces that pole. Okay, although you cannot see it directly here, I'm going to go ahead and put one just to demonstrate, and I'll make this 1 decade smaller. This, I really don't need this capacitor because I have another capacitor down that acts as a pole as well. So I'll make this 10 times smaller than this resistor. And now I want to take a look at the frequency response of this. So I bring this back in and I put it here at back where it was, and I bring the out and I bring it right there. So this is this part. So basically this is in and this is out, and I'm basically I am injecting a signal and I'm measuring the frequency response of that. So let's go ahead and take a look. And there you go. So let's zoom in, and we'll zoom in right here. Okay, if you notice, this is an integrator. So here is a 0 and then later on you have a pole. Okay, so you can see that looks very similar to what I mentioned. Okay, and now we want to take a picture of your Opto coupler. Okay, so how would we do the Bode plot of this? Well, this side wiggles, and when it wiggles, it causes the current to increase and decrease at the LED, and therefore it also causes current to increase and decrease at the emitter. So, and since this is the output, then we can move this to this side and bring the in to this side. Okay, so now in my statements that I said prior to that, I said that the Opto coupler was what restricted the bandwidth, and that it looks like a low pass filter. So it should look something like this, and then like that. Okay, so this is gain, and of course this is frequency. So you're gonna have a pole, and now this pole is internally. Okay, and one thing that we need to look also, we need to look, is it negative 20 dB, which is a first order, or do you have sections where you have negative 40 dB, which would be a second order? So that would be something that we would want to measure and take a look. So if you look, make Bode, and here's the bandwidth or the frequency response of the Opto coupler. Okay, and if you notice, it's got a little bit of gain, and then it has a little bit of gain because of the error app. There is a little bit feed through, and then it starts dropping. Okay, so let's measure this if we can, the slope. Okay, and if you notice, this is 38 dBs. So this section is a negative 40 dB. It's a second order system. So up to here is where you see the first order. So basically it's a filter that has a first order, it has a pole here, and then it has a second pole here. Okay, so that's what this optocoupler does. Okay, so basically now we have all our measurements, or our plots. Okay, and when you put all of these together, you get a total loop that looks like this. Now I'm going to go ahead and stop here because I wanted to first show that to get this, that you can take the Bode plot of subsections. In other words, we took the plant, the error app, and then the optocoupler, and when you put it all together, you want a loop composition that looks very similar to this. Okay, so I'll go ahead and stop here, since I showed the method and you have an idea, and then in the second or the next video I will show you how to select these values and these values. Okay, there's a capacitor that we can use here, or we can put another capacitor here to compensate. And in the compensation technique is very simple. Basically, you want to cancel poles and zeros. Okay, so we'll go ahead and stop here, and if you like what I have presented, please subscribe, share, and give a thumbs up. Thank you for watching.